Good evening, everybody in Bradford. I'm Steve Barrett from the University of Liverpool. I work in the Department of Physics, but astronomy has been a lifelong interest. Those two have come together occasionally, and this is arguably one example in which my interest in astronomy and my interests in understanding the universe have overlapped. So this is Ancient Light. You can see from the subtitle that what I'm talking about is imaging a quasar, a nucleus of a galaxy that's very, very luminous, imaging a quasar but without using a telescope. So you could say, in a sense, this is astrophotography on the cheap, if you want to think of it that way. So this started back in 2020. Because, as we probably remember, because it was only a few years ago, back in 2020, life changed. Life in lockdown. This particular object, this virus, led to the appearance of lots of these things dotted around various floors and pavements all over the country. Looking down at our feet, we were told to keep our distance. But at the time, I thought of Stephen Hawking's comment, remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. I thought that's interesting. Instead of looking down and keeping 2 meters away from my fellow humans, if I look up, what is the greatest distance I can possibly capture with my camera? Now, we all know that big telescopes are able to see objects that are very, very distant. But what about just my camera in my back garden? So we know that the universe is vast and the universe is ancient. And we know that large telescopes around the world and in space have imaged galaxies that are many billions of light years distant. But I was asking myself, is it possible to capture an image of one of these very remote objects without using a telescope? And spoiler alert, the answer is yes. Otherwise, I wouldn't be giving you this short talk. So it started when I read this particular paper. I'm not going to go through the details, but this was a paper that dealt with a survey of quasars. They were cataloguing and listing lots of quasars as seen by professional telescopes. Now, a quasar is the nucleus of a galaxy that emits enough light to be visible over a distance of billions of light years. Any galaxy that has a very active nucleus, a so-called active galactic nucleus, or AGN, probably produces enormous amounts of energies, and quasars are simply the most energetic class of active galactic nuclei. What's the energy source of these objects? Well, it's almost certainly a supermassive black hole. We don't know what they look like up close because none of them are up close. This is an artist's impression of what a quasar might look like. A supermassive black hole, lots of matter falling into the black hole. It might be gas, it might be dust, it might be entire stars. And the energy of that infalling matter is converted into visible light as well as radio waves and other parts of the electromagnetic spectrum. So we think supermassive black holes are the engine that produce this enormous amount of energy. And that's what makes these things visible. So reading this survey of quasars, I thought, which quasar might be possible to catch? We're in July of 2020. We're in the middle of summer. So I looked at all of these quasars, looked at their coordinates and found one that was high in the sky during the summer months as seen from the UK. I also wanted to find one that was as distant as possible, just to push the limit of what I think I can possibly capture with my camera. So I found a candidate. I found a quasar that was visible, high in the sky in July from the UK. It goes by the wonderful name of J16173. Yeah, you've got it there written in the top left-hand corner. The name is simply its right ascension and declination written out. There's no point in giving it a more prosaic name. And in this particular survey, the people capturing the information from these various quasars, not only have catalogued their positions, but have also given a spectrum. Not a very spectacular spectrum, perhaps. We see here the amount of light emitted from this object from blue at the left-hand end of this spectrum to red at the right-hand end. The scale here is in angstroms. Perhaps you're more familiar with nanometers, 400 to 700 nanometers in the visible spectrum. An angstrom is a tenth of a nanometer, so that's 4,000 to 7,000 angstroms. But the interesting part of this spectrum is a feature that was identified as belonging to a source that would be emitting at a wavelength of 1200 angstroms. And yet it's seen in this spectrum at a wavelength of about 6,500 angstroms. In other words, it was established that this particular light had been redshifted by that amount from originally 1200 angstroms, which is the wavelength it would have had if it was at rest relative to us, but because it's part of an expanding universe and is receding away from us, the light has been redshifted or stretched from 1200 to 6500. And we quantified the redshift by saying how much has it changed relative to its original value. So if it was 1200 when it left the object and it's now been stretched to 6500, we take the ratio of how much it's been stretched, the difference between 6500 and 1200, and we divide that by the original wavelength of 1200. So 65 minus 12 divided by 12 gives us a redshift of 4.3. Now 4.3 for a redshift means that this object is very remote. And I'll be talking about how we actually calculate distances in a few slides' time. All we need to know at the moment is that this is a very remote object. So, how did I go about trying to capture it? Well, I put my camera, I use a Nikon camera, I put it on top of a tracker. This particular tracker was an Ioptron sky tracker, the white box here. If you don't want to buy a sky tracker or any type of star tracker, you can build one for yourself. I built a star tracker for about £25 or so. They're not particularly expensive. If you want to get into astrophotography, a star tracker is a great way of doing that. So a tracker is basically just a box whose job is to rotate the camera at 1 revolution per day to counteract the rotation of the Earth. So if it's set up correctly, and that's why there's a polar scope in the corner of the tracker, a polar scope makes sure that the axis of rotation of the tracker is aligned with the axis of rotation of the Earth. So the tracker will then move the camera counter to the Earth's rotation, and hopefully the star field that it's looking at will remain relatively fixed. I chose to use my Nikon camera and a telephoto lens, a 300mm f4 telephoto lens. That's a lens and camera that I've used many times in the past, not always for astrophotography. One of my other hobbies is wildlife photography. And there's a picture of a lion taken a few months ago when I went on safari in Africa. The same Nikon D7500 digital SLR with the same 300mm f4 lens. I like that particular lens simply because it's relatively small and compact. You can see it there pictured in somebody's hand. And it means that if I go on safari, I don't have to take an enormous telephoto lens in order to capture pictures of animals at some distance away. Because, of course, when you're taking pictures of lions, you want to be at a safe distance. So you want a reasonable telephoto lens, but you don't want a lens that's too big or too heavy. And the 300mm lens does the trick for me. So, just to reinforce the point, I'm using a camera and lens that is the camera and lens that I use for all other daylight photography. The camera is not customized. The camera is not modified for astrophotography. It is a camera that's designed to take pictures in daylight. It's designed to take pictures of your cat or a landscape or a lion or a set of zebras. So if the camera and lens are designed and can indeed be used to photograph zebras, can I use exactly the same photographic setup to also photograph a quasar that's on the other side of the observable universe? There's no particular reason why a camera designed for daylight use should be so good for astrophotography, but I have found that modern technology is absolutely wonderful. So, the quasar that I chose out of this survey that I read about was in the constellation of Draco. And for those who know their constellations, Draco is high in the sky during the summer months, so that was ideal. I wasn't looking towards the horizon through a lot of atmosphere, I was looking almost straight up. So there's the constellation of Draco, next to it is the constellation of Ursa Minor, and there of course is Polaris on the right hand side. There's the field of view of the 300mm lens, and the dot in the middle is not the quasar. The quasar is far too faint to show up on any star map or star atlas like this. The dot in the middle just happens to be a star that's roughly speaking in the same position, just by pure chance of line of sight. That was quite handy because it meant that when I was pointing my camera at Draco, I simply had to find that particular star called AT Draco. It's a 5th magnitude star. If I found that, I knew that the quasar was not far away. So I pointed the camera at that particular star, set it up on my tracker, and then took the longest exposures I could get away with. I didn't want to take one long exposure, I took a whole series of short exposures. And this is in July, so of course we don't have a great deal of night during July. From evening twilight, the end of evening twilight, to the start of morning twilight is only about 2.5 or 3 hours at most. So I actually set the camera to take a whole load of 30-second exposures and let it run for about 2 hours or so. I actually took about 2.5 hours in total, but some of those had to be thrown away because some clouds came over and I just left the camera running rather than stopping it during the clouds. So I just continued taking pictures and then afterwards threw those particular images away. There was also the occasional satellite and the occasional aircraft flying past. Again, those were thrown away and all the remaining exposures were added together to give me the equivalent of one long 2-hour exposure. And this is the full field of view. There's the 5th magnitude star AT Draco in the middle of the field of view. I focused on one of the fainter stars to try and get the focus as accurate as possible. But I figured that once I had obtained this picture, all I needed to do was zoom in to the coordinates where I knew that particular quasar resided based on its coordinates from the survey that I'd read. So that's where it should be, in the middle of that square. So I took the image and blew it up. And there, right in the middle of the square, that is the quasar. I checked by running some plate solving that that is exactly the coordinate as specified by the survey to a fraction of an arc second. So that quite definitely is the quasar. When we look in detail, we see that most of the light from the quasar is focused into just 1 pixel. So if we blow it up, we don't see a great deal more. That's a blow up of the quasar itself. I've artificially lightened it and increased the contrast slightly. Perhaps you can see that some of the background stars are now starting to show in this particular view of it. Most of the light has gone into that central pixel. Perhaps a little bit is spilling out into the neighbouring pixels. So the quasar is just 1 pixel out of the 20 million pixels that the Nikon delivered to me. Only one of the pixels is interesting as far as I'm concerned. Just as an aside, what could we expect from this particular setup? If we've got a lens with a particular aperture, we can work out the resolution that we would expect to be able to get. The 300mm f4 lens, we can work out the resolution. It turns out to be, if it was perfect, if it was absolutely aberration free, we would expect to be able to resolve 9 microradians, 9 millionths of a radian, or if you prefer that in arc seconds, a little less than 2 arc seconds. And if we think about how large the pixels are in the camera, again with a 300mm lens, we can ask what area of sky or what angle does 1 pixel cover, and each pixel would cover about 15 microradians or about 3 arc seconds. So if the lens is good quality, it ought to be able to focus the light into 1 pixel. And just for a matter of comparison, at a distance of a few billion light years, how big would the Milky Way galaxy be? It would be of order a few arc seconds. The seeing conditions on this particular night were probably no better than a couple of arc seconds anyway. So the resolution of the lens and the camera and the seeing conditions were altogether very similar to each other. So perhaps it's no surprise that as long as you're careful, it is possible to get all of the light into 1 pixel of the image. When I looked at this, apart from recognizing that I had captured the light from the quasar itself, I also realized there were other things going on. I realized that by comparing this with some professional surveys of galaxies, I realized that a number of other objects in the field of view were also galaxies. Some of them we can recognize as galaxies because they're not strictly speaking circular. These quite definitely are non-circular objects. But there are quite a few distant galaxies where we really can't tell if they are faint stars or faint galaxies. And I had to rely on the coordinates given by other surveys to tell me that those were galaxies. So this 8 arc minute by 8 arc minute crop that I'm showing you contains 10 galaxies in total apart from the quasar itself. So if you scale that up to the entire image, that means that the image probably contains about 7,000 galaxies. There's nothing particularly interesting about the Draco constellation. If I'd pointed it to a different patch of sky, again, I probably would have picked up many, many thousands of galaxies. Which is why I, rather tongue-in-cheek, call this the Barrett Deep Field. So let's return to the idea of having imaged this quasar. How far away is it? What is the distance to the quasar? Well, we can think of the light leaving the galaxy. Here I'm just showing the quasar just schematically as a spiral galaxy. If the light left the galaxy, how far away was the galaxy when the light left? We can talk about the distance then. The distance to the galaxy when the light left the galaxy. But of course it takes a finite length of time for the light to reach us. And whilst the light is on its way to Earth, the universe is continuing to expand, which means the galaxy is receding from us and would be even greater distance whilst the light is in transit. And then we can think what would happen when the light reaches Earth. In other words, when the picture was actually taken, the galaxy has moved yet further away. And we can think about the distance when the light has actually arrived at Earth. We can think about the distance to the quasar now. So we have a distance then, and we have a distance now, and we have the middle distance, which is the distance the light has travelled, which is neither the distance then nor the distance now, but somewhere in between. So when we talk about the distance to the quasar, what do we mean by the distance? Which of those 3 distances are we referring to? Well, generally speaking, it could be any of those 3. Depends on the context of what you're talking about. But bear in mind, it's rather difficult and rather tricky to get your head round what's meant by how far the light has travelled. Because remember, whilst the light is travelling, space is continuing to expand. Not necessarily at the same speed as time goes by. So when we think about the distance that the light has travelled, that's a rather tricky thing to get your head around. Especially when some galaxies can be receding from us faster than the speed of light. It's like swimming against the tide. Light is travelling through space, but space is itself getting dragged backwards because of the expanding universe. So it's like a swimmer swimming through water, but the water itself would be dragging the swimmer backwards. Or another analogy is light travelling through space when space is expanding is a bit like an ant travelling along a rubber band, and somebody is stretching the rubber band as the ant is moving, as the ant is walking along the rubber band. So trying to work out how far has the ant moved is rather tricky because the ant is moving relative to something which is itself moving. And so that's a rather tricky thing to calculate. And the only way of actually calculating how far the light has travelled, or indeed how far the quasar was when the light left and how far it is now that the light has arrived, we have to have some knowledge, or at least some assumptions, about how the universe is expanding. So the way the universe expands, the way it evolves, depends on how much matter and how much energy there is in the universe. And that's still a matter of some debate, but there is some concordance agreement. We think we know how much matter and energy there is in the universe, and hence we've got a reasonable model for how the universe has been expanding since it was made in the Big Bang. And if our model is correct, we can then work out how it's expanded in the past, and hence we can work out for any galaxy at any distance from us, how much would the light have expanded on its journey from the galaxy, from the quasar, until it reaches us. If we know how the universe is expanded, we can calculate how much the light would have been stretched. In other words, we have a relationship between distance and redshift. And so I used that mathematical relationship to try and calculate the distances to this particular quasar. And I came out with a spreadsheet that gave me these sorts of curves. The red, the green and the blue are the three distances I've been talking about. The blue is how far away was the object when the light left the object. The green is how far has the light travelled, the light travel distance. And the red is how far away is that object now. If the object is very close to us, this bottom left-hand corner, very small redshifts, let's say a redshift less than 0.1, you notice that all these three distances are essentially the same. If the object is very close to us, the light doesn't take that long to reach us, and the universe hasn't had time to expand much in the length of time it takes the light to reach us. But as we go to larger and larger redshifts, these three distances diverge from each other. So we're not interested in all of these distances. We're interested in an object with a redshift of 4.3. So let's put that one in explicitly. There's 4.3 and the three distances of distance then, distance travelled and distance now. And those three numbers turn out to be these three numbers. 4.6 billion light years, a light travel time of 12.4 billion light years, or a distance of 12.4 billion light years, and a distance now of 24.6 billion light years. Let's just get rid of the curves because we don't need the curves anymore. So let's remind ourselves of what those three numbers mean. The quasar that I imaged was about 5 billion light years away when the light was emitted from the quasar. And the light from the quasar has been travelling for 12.4 billion years to reach us. Bear in mind 12.4 billion years. Remember, the age of the universe is 13.8 billion years. So the light from this quasar has been travelling for about 90% of the age of the universe. In other words, the universe was only about 10% of its current age when the light left. But for all of those 12.4 billion years, the universe has continued to expand. So whilst the light was travelling, the universe expanded, and so the quasar is now about 25 billion light years away. And when you look at these numbers, you come to a very interesting conclusion. The distance to the quasar has changed over a period of about 12 billion years or so. Over that time period, the distance to the quasar has changed from 5 billion to 25 billion light years. So the change, when we do a very simple back of the envelope calculation, during 12 billion years, the quasar distance has increased by more than 12 billion light years. Speed is distance over time, so just taking a very rough and ready average, if we take the total distance over the total time, the distance has increased by 20 billion light years, and it's taken about 12 billion years to do that. So the speed is 20 over 12 light years per year, or a little bit over 1.5 times the speed of light. That means the quasar has been receding from us, and indeed it was receding from us faster when the light left and is still receding from us faster than the speed of light some 12 billion years later. This does not disobey any rules of physics. Remember, the speed limit of light is only a speed limit of light or speed limit of objects travelling through space. We're not talking about travelling through space, we're talking about the universe expanding and the galaxies are getting carried along with the expansion. So the recession velocity of this object on average is more than the speed of light. But again, if we return to the mathematical model and say, well, we think we know how the universe has been expanding because we know how much, or at least we've got a pretty good handle on how much matter and how much energy there is in the universe, not only can we work out an average, we can actually work out the speed as a function of time. And it turns out to be something like this. The light left the quasar some 1.5 million years after the Big Bang. This is time relative to the Big Bang, so that's us here and now 13.8 billion years later. So the object was receding from us at 2.2 times the speed of light when the light left, and it's now receding from us at 1.7 times the speed of light, according to our understanding of the expansion of the universe. But notice the shape of that curve. The expansion, or at least the recession velocity of this object, appeared to be slowing down for quite a few billion years. But in the last few billion years, it's been accelerating. This is something that we didn't really know about if you go back more than 2 or 3 decades. It looks like the expansion of the universe is accelerating, and things switched over roughly here where the cursor is, some 7 or 8 billion years after the Big Bang. So it's perfectly reasonable that the object was slowing down. That's what we would expect. If gravity is pulling on everything as it expands, we would expect gravity to slow down the expansion. But this idea of this uptick, this upturn at the end, where the expansion appears not to be slowing down, but actually accelerating, this came as a big surprise when it was discovered 20 or so years ago. It's really bizarre if we try and make sense of that and say, if we plot out distance and time, this is the distance away from us, the distance from us, so 0 is us, and the vertical axis is time, and this is time since the Big Bang. So 0 is the Big Bang, and we are here at 13.8 billion years later. So if the light left the quasar when it was at a distance of about 5 billion light years from us, and it did so 12.5 billion years ago, how did that light get from the quasar to us? Now, naively, we would say, well, the light left the quasar, and then after a little while it got closer, and then after a little while it got closer still, and then after a little while it got closer still, and we would naively assume that the light simply travelled closer and closer and closer to us until it finally arrived here. But no, it can't have done that. The quasar, at 5 billion light years from us, was receding from us faster than the speed of light. So if it's receding faster than the speed of light, nearly twice the speed of light, sorry, a little over twice the speed of light, that means the light was actually getting dragged backwards. So if we look at what happened in the first few billion years, after the light left the quasar, a billion years later, it was actually further away from us. And another billion years later, it was still further away from us. Only after, 2.5 billion years or so, did the light finally start to make some headway and then eventually make it to us, here and now. And the fact that that's what the light path looks like in terms of distance and time is one of the weirdest things about this particular exercise of imaging this quasar. The idea that light can get dragged backwards because the object is receding at twice the speed of light, but still eventually the light will make it. What's happening to the quasar? Well, the quasar, not the light from the quasar, but the quasar itself, its distance from us continued to get larger and larger and larger as the universe continued to expand. I put it there as a dotted line rather than a solid line because remember, the speed of the quasar, the recession speed of the quasar, is not strictly constant. Remember, it was 2.2 and times the speed of light, then it fell a little bit, then it went up again. So really, this shouldn't be a straight line. Distance versus time should actually be a little bit of a wiggle. And I can't work out which way the wiggle should be, so I've just drawn it as a rough artist's impression, reminding us that the distance to the quasar continued to get larger and larger and larger and larger until somewhere over on the right-hand side, its distance is now some 25 billion light years from us. And the light took this ridiculous journey of getting further away and then eventually making its way to us. So the journey that the light has had is amazing and weird. The light was emitted, if we think of it from the perspective of the light was emitted 1.4 billion years after the Big Bang. And it had already been travelling for 8 billion years, even before the Sun and the Earth were born. And then it continued on its journey for another 4.5 billion years. Life evolved on Earth and the light travelled on. Dinosaurs came and went and the light travelled on. In the last million years of its journey, it arrived at the edge of our Milky Way galaxy, crossed a few spiral arms and entered the solar system. In the last few hours, it would have finally arrived at Earth, travelled through the atmosphere in a fraction of a second, hurtled towards England, dodged a few clouds, and then entered the lens and hit the camera sensor. It's only 1 pixel in the image, but what a journey that light has taken. So here's a graphical summary of what I've just been talking about. I put my camera and lens on top of a star tracker. You can build one for yourself if you like. This particular one was an Ioptron star tracker. I took a series of short exposures, pointing the camera at this part of the constellation of Draco because the survey I read told me that's the coordinates of the quasar. The main image tells me that this is the nearby star AT Draco and the quasar should be right next door, and a blow-up of that region shows me that yes, I have managed to capture the light from this quasar. The light travel distance of 12.4 billion years is a huge fraction of the total length of time that the universe has existed. The Hubble Space Telescope is able to look back to 13 billion years. I've managed to look back 12.5 billion years just with my camera on a tracker. And this object is now at the mind-boggling distance of nearly 25 billion light years. So, is it possible with a camera designed to take pictures in daylight to capture the light from a supermassive black hole at the centre of a galaxy on the other side of the observable universe? Yes, it is possible to capture what I like to think of as this quasar's ancient light. Thank you for listening.